In this video, we're going to learn how to solve polynomial equations. The first method we can sometimes use is grouping. This only works when you have a polynomial with an even number of terms, and when you recognize that there's a greatest common factor for the first set of terms and the second set. So here it's already written in standard form. If it's not, try putting it into standard form first. And now if we look at this, we'll see that x cubed and 6x squared have a GCF of x squared. Negative 4x and negative 24 have a GCF of negative 4. When you pull out the x squared from the first two terms, and when you pull out the negative 4 from the last two terms, you would end up with this. If you now look at this, x plus 6 is your new GCF for the first half and the second half. So this method doesn't always work, but if you can recognize that there's something in common between the first two and the second two, then you can try grouping. Now that we've done this, we'll again take out our GCF. So if you pull out an x plus 6, you'll be left with x squared minus 4. Now that I've done that, I can finish factoring this. So factor your difference of squares. If you then were to set each factor equal to 0 and solve for x, you would get that x is negative 6, negative 2, or 2. Another method we can sometimes use is to recognize a polynomial as being in a quadratic form. So this only works when you have 3 terms. It could work with a difference of squares, but usually you're going to see this with 3 terms. And you have to recognize this as actually being a quadratic. And what I mean is there has to be a constant term, a term with a variable, and a term with that variable squared. So you're used to seeing a quadratic where you have a number in x and an x squared. Here we have a number in x squared and x to the 4th. And you have to recognize that x to the 4th is really x squared squared. So one method you can use to solve these kinds of equations is make a substitution so it's easier to look at. So if the x squared and x to the 4th is throwing you off, rename it. You could rename it by saying let s, or any other kind of variable, be x squared. And then you would write it as s squared minus 7s minus 8. Then you can go ahead and factor this, like we're used to for quadratics, and you would get this. Now that you factored it, you must resubstitute back in the variable in the original problem. Again, s was just something we came up with, so put back in x squared, and then we would continue solving. Now if you're comfortable with how to go from here to here, then you don't have to use this substitution, but it's a method if it looks too complicated for you. So at the very end, we would set each factor equal to 0 and solve for x. So in the first part, we'd get that x squared has to be 8. So when we take the square root of both sides, x is plus or minus the square root of 8. And 8 is really 4 times 2. So since it has a perfect square factor of 4, you want to take the 4 outside. And when you take it outside, you take the square root. So you would get 2 root 2. The second part, if we take the square root of both sides here, we'll get that x is plus or minus the square root of negative 1. Now think back to algebra 2. The square root of negative 1 is how we define the imaginary number I. So this is really plus or minus I. So anytime you have a square root of a negative, you're now going to write those roots as the imaginary roots. Last method we can use is the rational root theorem. We're going to first discover what that is. So let's say we had the equation 6x squared plus 13x minus 5 equals 0. If we use guess and check factoring, we could split that up into 2x plus 5 times 3x minus 1. If you want to double check why that works, FOIL this out, and you'll see that you do end up back where we started. Now that I've done this, if I wanted to, I could pull out a 2 from the first factor, and I could pull out a 3 from the second. And when I do that, to take out a 2, 5 isn't divisible by 2, so I just write it as 5 over 2. If I pull out a 3, that 1 at the end becomes 1/3. This is really just a product of 4 things. I have 2 times this factor times 3 times that factor, so I can multiply the 3 and the 2 first and leave it as a 6 out front. If you now look at this, now that it's factored, your two solutions would be -5/2 and 1/3. If we think about -5/2 and 1/3, what do you notice about the numerators of those roots and the constant term? So the numerators were a 5 and a 1. That constant term is 5. So they're actually factors of the constant term. What do you notice about the denominators of the roots and the leading coefficient? Well, the denominators are 2 and 3. Our leading coefficient is 6. So they're, again, factors. So what we're starting to see is any kind of polynomial, when you factor it and you have rational roots. Again, rational roots are numbers that can be written as a fraction. So any whole number like 3 or any kind of fraction or terminating decimal, those are all rational roots. This doesn't include radicals and it does not include imaginary roots. But for the rational roots, where they come from is when they're written as a fraction, the numerators come from the constant term and the denominators of those fractions come from factors of the leading coefficient. So that pretty much is the rational root theorem. It just says that the possible rational roots for polynomial are of the form p over q plus or minus, where p are the factors of the constant term and q are the factors of the leading coefficient. So if you forget which one's over which, you can always try to think back to an example like this and how the denominators are from the leading coefficient and the numerators are from the constant term. So we're going to use this in an example now. So we're given this equation. Clearly it's not a quadratic form, it has way too many terms. Grouping's also not going to work right away because it's not an even number of terms, and there doesn't seem to be anything in common if you chopped this up. So we're going to have to use the rational root theorem. So first, we want to list the possible roots. So again, it's positive or negative, the factors of the constant term over factors of the leading coefficient. So factors of 6 are 1, 2, 3, and 6. Factors of 4 are 1, 2, and 4. And now what we're going to do is we're going to go through all the possible combinations for these fractions. So you have to kind of pick a system to make sure you don't forget anything. I normally start with one factor in the numerator and then put it over all the denominators and then move to the next one. So if I start with the 1 up top, then I'd have 1 over 1, 1 over 2, or 1 over 4. If I then go to the 2, I'd have 2 over 1, 2 over 2, but 2 over 2 is 1, which we already have, so you don't have to write it again. And then I'd have 2 over 4, which reduces to 1/2, which we again already have. Then I'd have 3 over 1, which is 3, 3 over 2, 3/2, 3 over 4, 3/4. Then I'd go to the 6, I'd have 6 over 1, which is 6, 6 over 2 is 3, we already have a 3, and 6 over 4 is 3/2 when reduced, which we already have. So basically you're just trying not to write any repetitions. So now these are the possible rational roots. Now, you could synthetically try to test through all of these. That would take forever. So what we're going to do is we're going to graph this polynomial. We're going to look at the graph, and we're going to try to determine which of these rational roots we can see. Again, if there are imaginary or radical roots, like we actually do have in this problem, you won't see those on your calculator. So if you could see all the roots, you would just get them from your calculator and be done. But we're going to need this method for any kind of imaginary or radical roots. Now that we approximated those roots on our calculators as 1 and -3/4, we can synthetically divide by the factors they came from to find our remaining factors and to get our leftover roots. This will also help us verify that these actually were correct too. So if you took your original equation and you divide by 1, since x minus 1 is our factor, you'd end up with this. Then do the next layer of synthetic division with -3/4, and we'd end up with this quadratic at the end. 4x squared plus 8 equals 0. So now we're going to solve this. You can't factor this. If I tried to isolate x, I would move the 8 over, and I'd have 4x squared equals -8. Then I would divide both sides by 4, and I'd have x squared equals negative 2. Now I could take the square root of both sides. I'd have x equals plus or minus the square root of negative 2. The square root of negative 2 you can think of as the square root of negative 1 times the square root of 2. Now the square root of negative 1, again, is the imaginary number. So we would get that x is plus or minus I root 2. Another way you could think of this is anytime you have a negative number under a square root, imagine taking out the negative and you end up with an I out front. So our final answer for all the solutions to this equation are the 1 and the negative 3/4 that we got from our calculator, and then plus or minus I root 2. So again, if you could graph this and see all the rational roots on your calculator, you wouldn't have to do this last step. You wouldn't even have to really think about those possible roots. But what you want to do is remember that there are going to be more solutions sometimes than you can see. And if your calculator gives you a really long decimal, that implies that it's some kind of radical root. So what you want to do is find the rational simple roots, divide by the factors they come from, and then factor at the end.